We discuss about modulus and conjugate of a complex number. So we start with a complex number here. You know that z equals to a plus ib is a complex number where a and b both are real numbers, that you know. This is called real part, this is called imaginary part. Okay. Then the modulus of z is denoted by this symbol, same what we have in real numbers, modulus of z, and is defined as modulus of z equals to square root of real part square plus imaginary part square, that is b square. This is the definition of modulus. That is, you can write modulus square equals to a square plus b square, real part square plus imaginary part square. This is the definition of modulus. For example, let's take z equals to 3 plus 4 iota, 4i. This is a complex number. So therefore, the modulus of z equals to root of real part square 3 square plus imaginary part square, that is 4 square, not 4 iota square, remember, a square plus b square. So this is nothing but 9 plus 16, 25. So this is just 5. This is the magnitude. This is also called magnitude, remember, magnitude of the complex number. Magnitude or modulus, both are same. You can call the magnitude or modulus, both are the same words, remember. One more, suppose I have this. Let's take z equals to 4 minus iota. So what is modulus z here? Root of 4 square plus here minus 1 square, remember. So I'll get the root 70. If I have just this much only, let's take z equals to just iota. So this is 0 plus 1 into iota, like this. So therefore modulus of z equals to root of 0 square plus your 1 square, which is just 1. Okay. So this is 1. Now we define conjugate. We want to define conjugate of a complex number next. Conjugate of a complex number. Let's take z equals to a plus iota b. This is a given complex number. Then its conjugate is denoted by z bar, your bar symbol, and replaced I by minus I. So a minus iota b, this is a conjugate. Replace I by minus I, this is the definition. Right? If I take one more time conjugate, if I take conjugate twice, then again here replace I by minus I. So this is a plus iota b. So this is z. So if you take conjugate twice, you will get the complex number itself. Fine? For example, let's take z equals to 4 plus 3 iota. Therefore, z conjugate equals to 4 minus 3 iota. I'll take z1 equals to, let's take minus 4 minus 2 iota. Then z1 bar equals to, that's the conjugate of z, minus 4 plus 2 iota. Remember, only the term involving iota would have opposite sign. Minus 2 plus 2 plus 3 minus 3. Definition is I is replaced by minus I. If I have this one, for example, z2 equals to, suppose I have this complex number, minus 4 by 3 plus 1 by 2 iota. What is its conjugate? Z2 conjugate equals to minus 4 by 3 minus 1 by 2 iota. I is replaced by minus I. This is the definition. Okay, so this is about conjugate. Now I'll just state some properties of modulus and conjugate. So let me write here some properties of modulus and conjugate of a conjugate of a complex number. We write some common properties. The first one is here, if you find the magnitude of any complex number is always greater than or equal to 0. Modulus never be negative, remember. Modulus of a complex number is always greater than or equal to 0. It never be negative, it can be 0. Okay. The second one, if you have product of two complex number, the entire modulus that is equals to individual modulus, remember, like this. So modulus of Z1 into Z2, that is equals to modulus of Z1 into modulus of Z2. Third one, if you have modulus of Z1 by Z2 equals to modulus of Z1 upon modulus of Z2. Z2 should not be 0, remember, it should not be 0 complex number. For product and division you have equality, but if you have addition, modulus of Z1 plus Z2, this for addition you have your less than or equal to modulus of Z1 plus modulus of Z2, remember. For addition you are not having equality. But it can be proved, we are not getting into this. For multiplication and for division you have equality. For addition you have less than or equal to. This is sometimes called triangle inequality. Triangle inequality. Not equality, this is inequality. Modulus of Z1 plus Z2 is less than or equal to modulus of Z1 plus modulus of Z2. Okay. The fifth one, if you do this, Z into its conjugate, if you do this, so you can verify. For example here, let's take Z equals to A plus iota B. What is its conjugate? A minus iota B. I'm multiplying this two, Z into Z conjugate. So product of these two, this is A plus B, this is A minus B. It's like x plus y, x minus y. So x square minus y square, that is IB whole square. X plus y, x minus y, that is x square minus y square. X plus y into x minus y, you know what is this? X square minus y square. So I'm using this here. A square minus y is IB, remember. So IB whole square. A square. Now you know iota square is minus 1, so this will be plus 1 and b square. What is this? If you remember, this is nothing but modulus of z the whole square. I told you here. Modulus of z the whole square is a square plus b square. So finally what I have shown is here, this is nothing but the modulus of z the whole square. This is very important property. Magnitude of complex number with whole square, modulus of a complex number with whole square equals to z into its conjugate. Always true. This is very important property, remember. Okay, now next is about conjugate. Sixth one, that is if you have z1 plus z2 the whole conjugate equals to z1 conjugate plus z2 conjugate. Even for minus it's also true, remember. Here you are adding first and then you are taking conjugate. Here you are taking conjugate first of individual complex number and then you are adding or subtracting, remember. So this is always true for addition and multiplication. The next property, that is property number 7 here. which is for multiplication. Z1 into Z2, the whole conjugate equals to Z1 conjugate into Z2 conjugate. And the same property is for division. Z1 by Z2, the whole conjugate equals to Z1 conjugate upon Z2 conjugate. This is always true, remember. Right? Only this triangular inequality is little bit different. This is little bit different. The others are straightforward. Magnitude or modulus of any complex number is always greater than or equal to 0. Multiplication of complex number, the whole modulus equals to individual. For division you can apply individual. For addition you have such inequality. Complex number into its conjugate is modulus of z whole square. For addition you can do individual modulus. For multiplication also you can do individual conjugate, and same way for division also you can do individual conjugate. I'll take one simple example just to verify. Let's verify these two. For example, let's take z1 equals to, I'll take 2 plus iota, and z2 equals to, let's write any randomly, I'm taking complex number, 3 plus 2 iota. I've taken this complex number. We want to verify, we verify this one, z1 into z2, the whole conjugate equals to z1 conjugate into z2 conjugate. Verification means what? You get LHS, get RHS, and you see that the both are equal. So on the left hand side you need to find z1 into z2 first. So 2 plus iota into 3 plus 2 iota. I'm just taking the product. 2 into 3, 6. This is 4 iota. This is 3 iota plus 2 iota square. 2 into this, you know. Now iota square is minus 1, you know. Here iota square is minus 1. So this is minus 2. 6 minus 2, which is 4 plus 7 iota. This is z1 into z2. Therefore, z1 into z2, the whole conjugate equals to 4 minus 7 iota. Keep on the left equation number 1. Call that as equation number 1. Conjugate of this complex number. Conjugate you can do only when it is in a plus ib form. So what I did, I've just simplified and I've shown that it is 4 plus 7 iota. So what its conjugate? I is replaced by minus iota, equation number 1. On the other side, on RHS, you have z1 conjugate into z2 conjugate. z1 conjugate means 2 minus iota into z2 conjugate means 3 minus 2 iota. Now just open the bracket. 2 into 3, 6. This is minus 4 iota. This is minus 3 iota. This into this plus 2 iota square. Minus minus plus 2 iota square. Now again this iota square is minus 1, you know. This is just minus 1. So 6 minus 2. So this is 4 minus 7 iota. This you can see 2. This is RHS. This was LHS, you know. This is LHS. So from 1 and 2 you can see that the both are equal. LHS equals to RHS. This is not the proof. Just I have explained how it works, remember. You can try the other properties also. You can try 8th property. You can try 6th property. Let's verify for the same example. Or let me take one new example. I'll take one more example and I'll verify the property number 4. So let's take one more example here. I'm taking z equals to 1 minus iota. z1 equals to, z2 equals to, let's write 3 plus 4 iota. Okay, and I want to verify the property number 4. We verify this one, modulus of z1 plus z2 is less than or equal to modulus of z1 plus modulus of z2. We want to verify this. So we find LHS, and we'll see that this is bigger than this. Okay, so first for LHS, get Z1 plus Z2, simple addition. So what we'll get here, 1 plus 3, 4, and minus 1 plus this, so this is plus 3 iota, minus plus 4, so this would be 3. Now get its magnitude. So modulus of Z1 plus Z2 equals to root of a square plus b square, 16 plus 9, so which is 5. This is 1, so left hand side is 5. Okay, now we go for RHS, right hand side. On RHS, on right hand side, we find modulus of Z1 plus modulus of Z2, and we'll notice that this is bigger than 5. What is modulus of Z1? That is root of 1 square plus 1 square, 1 plus 1, plus what is this? This is root of 9 plus 16. So this is root 2, and this is nothing but 5. So clearly you see a 5 plus something. This is RHS. LHS is just 5. What is RHS? 5 plus root 2. So therefore from 1 and 2, you can see that modulus of Z1 plus Z2 is less than or equal to modulus of Z1 plus modulus of Z2. This is a very well known property in complex numbers. This is called triangle inequality. Triangle inequality, remember, this is not equality. In certain cases you may have equal to, remember, this is less than or equal to. Sometimes you may have equal, but in general you can say that it is less than or equal to. Always they are not equal. Okay, the other properties you can verify. I'm sure you can do it. Now we move ahead for the theory portion. So next point is here, a representation of a complex number in a polar form. So here polar representation of a complex number, polar representation of a complex number. Okay, so we start with a complex number here. Let's take the complex number b. Z equals to, for example, I have taken here, let's take z equals to x plus iota y. This is a complex number. X is a real number, y is a real number. Okay. Now here, if you recall here, what is complex number? It is just set of ordered pairs of the type a comma b, where a and b be any two real numbers. And we already noted that every complex number z can be expressed in a plus ib form. And I told you whether you write a plus ib or whether you write a plus ib or ab, both are same. So this is always true. A plus ib is exactly same as ordered pair a comma b. Remember, both are exactly same. It can be proved. I'm not getting into that. But a plus ib is exactly a comma b. Remember, this is just way of writing. Either you can write the ordered pair or you can write a plus ib. So if I write this, for example, suppose I have this complex number. For example, if I write 2 plus 3 iota, it is simply 2 comma 3 as an ordered pair. Every complex number is an ordered pair of numbers. So 2 comma 3, which is as good as this, and every complex number can be expressed in a plus ib form. So we have this. Suppose one more, I have taken 4 minus iota. So this is 4 comma minus 1. I told you minus 1. Suppose next I'll write 1 plus iota. It is exactly 1 comma 1. Now these are nothing but what? Ordered pairs. These are the odd. So these are ordered pairs. Now you already studied probably in 9th and 10th standard, every ordered pair you can represent in the Cartesian plane. So if I show Cartesian plane here, x-axis, here y-axis for example, this is origin 1 comma 1. So 1 from here, 1 from here. So this is 1 comma 1. Suppose here 4 comma minus 1. So you know 2, 3, 4. 4 from here and minus 1 from here. So this is nothing but which ordered pair? 4 comma minus 1. This is another complex number. Suppose I have 2 comma 3, this complex number. So you know 2 from x-axis here and 3 from here, 2 and 3. So it is this complex number. This is nothing but the 2 comma 3. So this is a complex number, this is a complex number, this is a complex number. So every complex number, this is indirectly you can say that the 2 plus 3 iota. This is nothing but the 1 plus iota, you know. This is nothing but a 4 minus iota. That means every complex number can be presented in this Cartesian plane. This is our standard Cartesian plane. Right? Every complex number is an ordered pair. Every complex number can be presented on the plane, on the Cartesian plane, on the plane. And here such a plane is called complex plane. Complex plane. Or such a presentation of a complex number is also called such a complex plane is also called Argand diagram. Argand diagram. This is the name of the mathematician. Argand diagram. Right? So this is Argand diagram. Argand diagram means what? You present the complex number in the Cartesian plane. Suppose I have one more complex number. Let me write minus 1 minus iota. It is which ordered pair? Minus 1 comma minus 1. So minus 1 from here, minus 1 from here. So this complex number, minus 1 comma minus iota here. So presentation of a complex number in the Cartesian plane is sometimes called the complex plane or Argand diagram. Right? Fine. Whether I use the word simply plane or I use the complex plane, meaning is same because ordered pairs are nothing but the complex number. And such a representation is called here Argand diagram. Representation of complex numbers in a Cartesian plane is sometimes called Argand diagram. And here x-axis is sometimes called real axis. Real axis. This is sometimes called real axis. And this y-axis is sometimes called imaginary axis. Imaginary axis. Y-axis is sometimes called imaginary axis because here you see when you write for example 2 comma 3, then 3 is called imaginary part. It comes from y-axis. That's why it's called imaginary axis. 2 comes from x-axis, which is the real part. So that's why this is called the real axis. So x-axis is the real axis and y-axis is called the imaginary axis, remember. And such a diagram, I repeat one more time, such a diagram is called Argand diagram or just a complex plane or simply plane or Cartesian plane. Okay, now I'll come to the next point, that is here. Suppose I have this in general complex number. Let's take complex number z equals to x plus iota y. Now this you can represent in a Cartesian plane. So let's take, this is x-axis here, this is y-axis. Suppose this is a complex number. This is which ordered pair? X comma y, which is same as x plus iota y. This one. Okay, this is complex number z, you know. Here this is a complex number z. In a Cartesian plane, this is a Argand diagram representation or a complex plane. You know that this is origin. What are the coordinates here? 0, 0. Now you know from 10th standard distance formula, distance between these two. I'll get the distance. This is origin O. Let me call this as point P. So OP. What is OP? That is the distance between these two. If you remember distance formula, root of x1 minus x2 whole square, 10 standard, plus y1 minus y2 the whole square. Can you recall the distance formula? This is called distance formula. You know distance formula from 10 standard. You might have studied earlier. Distance formula. Distance between these 2 points. 0 minus x the whole square plus 0 minus y the whole square inside the square root. What is this? Just recall, this is nothing but real part square plus imaginary part squared with square root. So it is nothing but what? Modulus of complex number. So this is nothing but the modulus of z. Distance of the complex number from the origin. That's the modulus or magnitude. What is this? This is the distance of z from origin. From origin. And distance never be negative. It can be 0. So that's why we have written that modulus of any complex number is always greater than or equal to 0. Fine. So if I have another complex number here, for example z1, and if I find this, what is this? This one is nothing but the modulus of z1. Distance of any complex number from origin represent magnitude, modulus of the given complex number. It's a distance of z from origin, remember. Fine. Okay, one more. If I have z2 here, if I measure this distance, this is nothing but the modulus of z2. So this portion is nothing but the modulus of z2. Distance of any complex number from origin represent modulus. So we have this. Now about conjugate. This is about modulus. One interpretation. Let's take here z equals to 3 plus 2 iota. What is its conjugate? 3 minus 2 iota. I represent both in the Cartesian plane. You will realize what happens. See, this is 3 comma 2. So 0, 1, 2, 3. Here 3 and 2. That is 1 and 2. So this is 3 comma 2. This is complex number. So this is z 3 comma 2. 3 from here and 2 from y-axis. X-axis, y-axis. Now conjugate 3 minus 2. So 3 from here minus 2 from here. This is z bar, which is 3 minus 2 iota. Conjugate. Now what is this? If I keep mirror here, then you'll get this image. So conjugate is nothing but the mirror image around x-axis. What's a conjugate? It is. So conjugate, it's a mirror image about x-axis, right? If I have here a complex number, then its conjugate will be here. If I have at this place complex number, the conjugate will be here. If this is z1, then this is z1 conjugate. This both will fall on the same line. These both are falling on the same line. Remember, this is here z, distance from the origin, and you get this distance from origin. Both will be equal. So this is always true. You can verify magnitude of z and magnitude of its conjugate. Both are always equal, remember. If you find magnitude of a complex number and magnitude of its conjugate, both are always equal. Actually, I should add there in the properties. So I'll add there. You can put again in your class book. Your 9th number I can write. This is always true. Find the magnitude of a complex number and magnitude of its conjugate. These two are always equal, remember. I forgot to mention this, but these two are equal. Modulus of a complex number and the modulus of its conjugate are always equal. That's what we have noticed here, remember. This is always true. You can verify. Find the modulus of this. You can see that here modulus of this complex number is root of 9 plus 4, a square plus b square, which is nothing but root 13. What is modulus of z here? Z conjugate. You can see that, which is also here root of real part square, which is 3 square, plus imaginary part, which is minus 2 whole square. So 4 plus 9, this is also root 13. So both are equal. This is always true, remember. And what you have noticed, conjugate, it's a mirror image of a given complex number around x-axis. If you put mirror here, you will get the same reflection on the other side. So now this is another representation of a complex number, which is called the polar form. So we come to that. So I'll take a complex number z equals to x plus iota y. So you know now this can be represented on the Cartesian plane. This is called, organ diagram. X-axis, y-axis here. This origin. Suppose this is z equals to x plus iota y, for example. It can be anywhere in the plane, remember. If I join with origin here, you know that this become modulus of z. Distance of a complex number from origin, its magnitude. I'll call this angle as theta, for example, right? And I'll join this one with the x-axis. Okay, so here in this right angle triangle, if I take modulus z equals to, for example, small r, you know that this is the x. Horizontal distance is x, and you know that this is y. That for if it is x comma y, this would be y. So in this right angle triangle, you can write cos theta. What is cos theta in right angle triangle? Cos theta, adjacent upon hypotenuse. I have called this as r, that is x by r. What is sin theta in this right angle triangle? Opposite upon hypotenuse, that is y by r. So what is x from this? R cos theta. And what is y from this? R sin theta. I'll place these two values here in the complex number. So therefore z equals to x r cos theta plus iota r sin theta. I'll take r common, so z equals to r into cos theta plus iota sin theta. This is here polar form of the complex number. Remember, this is in form of r and theta. This is in r and theta, remember. What is r? That's the magnitude of a complex number. Don't forget this. R is actually magnitude of the complex number. What is theta? Theta is the angle made by this, O if I call this as P, this line segment with the x-axis. Now here, usually, theta can be any value, around the unit circle, if you imagine unit circle. But in general here, theta is taken from minus pi to plus pi. Where is minus pi on the unit circle? It starts from here. Minus pi is here. Minus pi to 0. And then 0 to pi, this way. So half rotation in this way and half rotation in this way. This is again pi. Minus pi and pi both are equal, remember. That's why strict sign here and less than equal to here, remember. The condition on the theta is taken in this way in complex number. This is very standard value. And here theta is called argument of the complex number. Argument. Theta is called argument, or sometimes it's also called amplitude. Amplitude or argument. Theta is called argument or amplitude of a complex number. When the concept is like this. See, when we are in upper half plane, suppose your complex number is here, then it should be taken in this direction. If this is a line segment, in this direction angle should be considered. This is angle theta. If it is in lower half plane, then it should move in this direction like this. So this become negative. That's why we have minus pi to 0 and 0 to pi. Value of argument theta should always come from this, remember, for complex number. This is very essential condition. Theta can be any value, but it normally should come from this. And here this theta is sometimes also called principal argument, main argument. Principal argument or main argument. Principal argument or main argument. Principal means main argument. Theta should come from these only, remember. We'll see by an example. Basically, what is that? That is the angle of the complex number with the x-axis, remember. If I ask you the simple question here, suppose complex number is somewhere here. Suppose I'll take complex number 0, 1. This is iota if you remember, beginning. So what's the angle of this one with the x-axis? You know that this is 90 degree. So theta is here pi by 2 or 90 degree. So this become argument here. So argument is this of given complex number. Clear? I'll discuss by formulas also, but I'm just simplifying what I mean by argument. Argument is the angle of the complex number with the x-axis. Suppose one more, I have complex number here, somewhere here. This one is my complex number. So this angle here, this angle gives us argument. This is theta, that is argument. Okay. If complex number itself is on the x-axis, suppose complex number is on the x-axis here, like this, it itself on the x-axis, then obviously theta will be 0. If I have complex number somewhere here, remember, suppose complex number is here, z. In that case, we will not take this angle, we will take this to this angle. If you are in the lower half plane, then we move in this direction. If you are in upper half plane, then this direction, remember. So if your z is somewhere here, complex number, then we will take this as a theta, remember. Not this one. No. Only this angle, this much. So when you are in lower half plane, that's what I'm trying to tell you. When your complex number is in lower half plane, then you move in this anti-clockwise direction. If your complex number is in upper half plane somewhere here, then we move in this anti-clockwise direction here, anti-clockwise direction here, this direction, remember. So therefore, the range, if you are from this to this portion, that is minus pi to here 0. Here minus pi in this direction, minus pi to 0. And when you are in this direction here, then till pi. So therefore the range of the theta is always from minus pi to pi for argument. So we use this, you will see. Okay. For example, let's take one example so you can understand. Here z equals to 1 plus root 3 iota. This is a complex number. What's the question? Question is, you express in the polar form. Express in the polar form, that is in r theta form, polar form, r theta form. So we find r and theta. So you know here r is modulus of z, which is root of 1 plus 3. So it is 2. So r is 2. Okay, now we find the theta. So for theta, we use this relation. Which relation? Cos theta equals to x by r and sin theta equals to y by r, as we have noted earlier, if you remember. We already noted that the cos theta is x by r and sin theta is y by r, if you recall. Cos theta is x by r, sin theta is y by r. We use this. Okay. Now what is x? X means the first coordinate, that is 1. So cos theta equals to 1 by 2 and sin theta equals to root 3 by 2. You want theta. Now find the theta for which cos theta 1 by 2 and sin theta root 3 by 2. So you know theta is pi by 3, or you can write 60 degree, both are same. So therefore now we got the theta. So polar form of the given complex number, that is z equals to, you know, r into cos theta plus iota sin theta. But what is r? R is 2. Cos theta, theta is pi by 3 plus I sin theta pi by 3. So we have this. This is polar form. Keep in this form only. Don't put the value of pi by 3 and sin pi by 3 and cos pi by 3. Otherwise you will get the same complex number. This is another way of representing the given complex number. Remember, this is called the polar form. One is polar form, one is this iota form, and one more, you know, that is ordered pair, which is, you know, this is nothing but which ordered pair? 1 comma root 3. These are the three ways to represent a complex number. Ordered pair 1 comma 3, 1 plus root 3 iota, or this. All these are the same thing, remember, but we are representing in different forms. Okay, let's take this for example here. Z equals to, I'll write that complex number iota. Now you know I want theta. The question is, we find argument, we find theta. Now I told you what is theta, that is the angle of this complex number with x-axis. Where is this complex number iota? You know 0, 1, it is somewhere here. What's this angle? You know that this angle is nothing but the pi by 2 or 90 degree. So our answer of theta has to be pi by 2. In the previous example, roughly, if I represent this complex number, this is just for your information, remember. This is which ordered pair? 1 comma root 3. So 1 from here, and root 3 is 1.73 somewhere here. This is a complex number. Z equals to 1 plus root 3 iota. You join this one with origin. Then this angle is this one, pi by 3. This angle is nothing but the 60 degree or pi by 3. Remember, this is the concept of angle, or what you can call the argument. So now your answer, you know, answer is pi by 2. Directly you can say by observation. But let's do by this method. We want theta. So here z equals to, you can write 0 plus iota. So x is 0 and y is 1. X and y is 1. Compare with which one? X plus iota y. X is 0, y is 1. Okay. So therefore r equals to modulus z equals to root of 0 square plus 1 square, which is 1. Okay. Therefore, what is cos theta? Cos theta is x by r, that is 0 by 1. And what is sin theta? That is y by r, which is 1 by 1. So this is 1. So what you are getting? Cos theta equals to 0 and sin theta equals to 1. Find the value of theta for which sin theta is 1, cos theta is 0. So obviously it is pi by 2, remember. So this is your argument. So if you want to write this complex number in a polar form here, the polar form is this. The polar form is here z equals to r. What is r here? 1. Cos pi by 2 plus iota sin pi by 2. This is your answer. If you simplify this, cos pi by 2 is 0, sin pi by 2 is 1. So obviously you'll get the I. But this complex number can be expressed in this form. So this is polar representation, right? In this chapter, this concept should be clear to you, remember. Concept of finding theta and r. So exercise 5.2. The first question is get about modulus and argument of the complex number. So first here r, which is modulus, which is root of minus 1 whole square 1 plus minus root 3 whole square, which is 3. So this become 2. So r is 2 here. Now to find theta, that is argument, we use cos theta equals to x by r and sin theta equals to y by r. We use this. So we have this. Now you see this is negative and this is also negative. That means this theta must be in the third quadrant. Recall, sin and cos both are negative. That means theta is in which quadrant? Third quadrant. Theta is somewhere here. Now as per our definition of argument, it should be more than minus pi and less than or equal to pi. So here theta equals to, first forget about this 2 minus sign. For what value of the theta cos theta is 1 by 2 and root 3 by 2, that is pi by 3, and you want this one, and here you have minus pi. So what I need to do? Minus pi plus something. So you have this. Why I wrote minus pi? Because if it is in the lower half, then I need to take this way. Now here you have minus pi. So minus pi plus pi by 3. So finally you are getting minus 2 pi by 3. This is the correct angle. Remember